Dear colleagues, my name is Evgeny Bondar. I'm from ITOM, Novosibirsk, Russia, and I'm going to talk about parallel DSMC implementation of the detailed surface chemistry mechanism. This work has been performed together with my lab mates, Alexey Litvintsov, Alexandra Molchanova, Alexander Kashkovsky, and Pavel Vashchenkov. The work is related to the problems of space vehicle high-altitude aerothermodynamics. Well, we know that at altitude above approximately 80 kilometers, the continuum approach is not applicable, and this is why we use the kinetic approach, normally based on the direct simulation Monte Carlo or DSMC method. Surface chemical reactions are very important for predicting the heat flux to the TPS surface of the re-entry vehicle. This is why we need to develop models for the DSMC method to simulate such processes. In our paper, Molchanov and co-authors, we proposed a general approach to construct such DSMC surface chemistry models on the basis of any detailed macroscopic finite rate chemical mechanism. And to apply this approach to the realistic computations of 3D geometries of real space re-entry vehicles, we need to be able to perform parallel computations, and this is why we need to parallelize this approach, and this is the main objective of the present work, to develop a parallel DSMC algorithm to simulate the surface chemical processes. Next is to implement it into the code, into the SMILE++ software system, which is a more modern version of the SMILE code. To verify these implementations and to apply it to some 3D vehicle computations. In this work, we consider the Apollo command module. Normally, the detailed chemical mechanisms of the surface reactions include such processes as adsorption, desorption, Illy-Riedel recombination, and Wilkinson-Wood recombination. We divide these processes into impact mechanisms and surface mechanism. Impact mechanism involve gas phase particles which interact with active sites or particles adsorbed at the surface, and surface mechanisms are processes which involve only particles adsorbed on the surface. This is important because we model these processes in the different parts of our DSMC code. It's quite natural to model these impact mechanisms inside the stage of the transfer of all particles on the time step. Usually we perform the gas surface interaction of these particles with the elements of the surface inside this step. This is why impact mechanisms are modeled here. But surface mechanisms which are between the absorbed particles, they are modeled at a completely independent stage of their DSMC algorithm. To simulate this process, we need to specify probabilities or frequencies of these processes which are required for the DSMC simulation, and we do it, as I've already mentioned, on the basis of their macroscopic data. So if this finite rate chemistry is formulated in terms of the reaction rates, which can be written in the Arrhenius form as a function of temperature. So then I start with the impact mechanisms. We can solve their inverse problem to obtain the probabilities of the adsorption or Illy-Riedel recombination to obtain probabilities of this process, and then we can directly use these probabilities in our DSMC simulations on the move step, as I mentioned. So we solve these inverse problems written in the following form. So we can obtain a macroscopic probability, average probability of all the molecules, which can be determined from the reaction rate constant, and we have in the right hand side the integral of the microscopic probabilities of probability of any particular particle with usually atom with some particular velocity to interact with their active site or with some particle adsorbed at the surface. So we assume here thermal equilibrium, and then we solve this integral equation and obtain this microscopic probability. So we use here the inverse Laplace transform and obtain these probabilities for adsorption, this written like this, and for Illy-Riedel recombination, which is written like this. And this approach can be considered as some generalization of the total collision energy model, which we use for the gas phase reactions. So we used these microscopic probabilities then in any non-equilibrium situation after obtaining them for assuming thermal equilibrium. What about surface mechanisms? So we use here some generalization of our usual DSMC schemes, which we employ for the gas phase collisions. So in particular, Langmuir-Hinshelwood recombination is modeled with a variant of measure and frequency scheme, and in particular desorption which is an individual process, and it doesn't involve a pair of particles, but it involves only one particle. But we use quite the approach which is quite similar to the usual null collision scheme, and both of these approaches in fact consider this that these elementary events follow the Poisson distribution, and time between processes is distributed exponentially, and we can use an expression like this to model the time to the next elementary event. In fact, in our approach we group all these events, all different Langmuir-Hinshelwood recombinations, and all the kinds of the desorption of particles of all sorts. We group them together and use their total frequency of all the processes to model the time to the next event, and then we pick the process proportionally to the frequency of this process, and we do it until the time step is finished, and as I mentioned, at completely independent stage. What are the problems with the parallelization of this approach to modeling surface chemistry? Let's recall how do we parallelize the DSMC computation. We normally use the domain decomposition here, and we assign each subdomain to some computational thread, and all the particles which belong to the subdomain, they belong to the thread. And after moving the particles, we perform the data exchange between threads, just transferring particles which move to the other subdomain. In fact, it looks here quite nicely, but the real picture can be something as a patchwork quilt, because sometimes we use random distribution of computational cells between threads for the sake of load balancing. So this is only a schematic here to show you the main idea. Look at the very important thing that normally we do not use body-fitted mesh. Many DSMC codes use Cartesian grids, and any surface element, any surface panel, triangle can even lie in different subdomains. And this is a really normal thing. And it's very natural that particles from different subdomains interact with the same element. We call these elements panels in our SMILE family codes. Moreover, even if the surface elements lie totally within some particular subdomain, we can have a particle which is coming from a different subdomain, from a different thread, which interacts with this panel during the time step. The problem is with modeling surface chemistry, as we should know the state of the panel. We should know the surface densities of the different species at the moment of interactions. We should know their surface density of vacant active sites. And these parameters are changing during the time step, during this move stage. When the moving particles, after each interaction, these parameters are changing. So the first solution is to try to update the state of the panel each time we have such a process as adsorption or Lie-Riedel recombination, and transfer this information to all other threads. But it looks not very feasible to perform this transfer after each event from the point of view of parallelization efficiency. Another option is to try to divide this computational trajectory in some sub-trajectories which belong to different threads. And in this case, we have different states of this panel, different populations of different species on the surface at the end of the move stage. And it's not really clear how to merge these sub-trajectories into one particular state of the panel. We even can have negative number of some particles on the panel, or we can have more particles than the number of active sites on the surface. And it looks like a problem. And if we take a look at the DSMC algorithm, we can see here that we usually perform this data exchange after the move step. And it's not feasible, as I mentioned, perform the data exchange inside the move step. It's really unfeasible from the computational point of view. And to deal with this problem, we proposed such an approach of completely dividing this computational trajectories in the sense that particles of one computational threads only interact with with some parts of the surface element and with active sites on this part of the surface element, and only with molecules adsorbed at this particular part of the surface element. So any surface element, any panel is divided between their computational threads. The problem is that the geometrical boundaries between these subpanels are not defined, because as you can see here, any particle can come to any part of the panel from any particular thread. This is why we use such a concept as virtual subpanels. The only thing which we need to define is the area of this subpanel, and number of active sites on this subpanel is proportional to this area, and also the probabilities and frequencies of the processes they involve this area. To determine this area, we just use the particles flow from each thread to the panel, and these areas are proportional to this particle flow. And to reduce the statistical error, of course, we average this particle flow data over some time. And using such an approach, as I mentioned, we are able to completely divide all the simulation processes between different computational threads. We use we exchange this data with some up when we obtain the surface processes, the overall surface processes, overall surface properties. Pardon me. As I've already told you, we can use any detailed chemical mechanism to construct the DSMC model using this approach. And we considered here several different surface mechanisms. First one is the mechanism for reaction cured glass of Deutschmann, Riedel, and Werner's. Second one is the mechanism of Kovalyev and co-authors for crystalline alpha alumina. And the third one is the silica mechanism of Kurataki, which is interesting because it includes the reactions of NO production, both during the Illy-Riedel recombination and Lindgren-Schulze processes, which also led to this NO production. And I will show you some code verification results for a single processor case for this particular Kurataki mechanisms. It is more complicated for the DSMC because it involves different reaction channels. For example, when O interacts with the surface, it can lead to creation of atomic oxygen or to the creation of NO. And verification is performed for such a model simple problem when the flow of atomic species interact with the wall without the gas phase collisions. The density is really low, which is typical for high altitude aerothermodynamics, and the temperature of this atomic gas is equal to the temperature of the wall. And in fact, we have such a thermal flow of atomic species to the wall, and the flow of reflected molecular species from the wall, which don't interact with each other. So we keep a we keep the density and the temperature of this atomic gas constant, and we vary temperature in the course of the computation. For such formulation, we can write down the balance equation for the different components for oxygen and nitrogen. And this is the example of the first computation, which involves only adsorption and desorption processes, and we see the perfect agreement and the fractions of active sites occupied by different species in the range of the temperatures from 500K to 2500K. Then we add the Illy-Riddell recombination, which leads to O2 and 2 production, and again the perfect agreement. And also now we include the reaction which result in production of NO, and again we see a very good agreement. Then we tried the Link-München-Schulwood recombination, only first 2 reactions. We see the great agreement here, maybe except for the very low temperatures, and Link-München-Schulwood recombination also with no production. Again, the very good agreements. And finally, this is the case which involves all the processes from the Kuratake model. And again, the agreement is great for the whole range of temperatures. And this is a particular verification of this multiprocessor algorithm. As you can see here, we have these theoretical curves, 1 processor case which is shown by circles, and 3 processor case which is shown by squares. And you see very great agreement between 1 processor and 3 processor case. Here we also, you can see, if you look closely, you can see this agreement because you see squares and circles, they coincide greatly with each other. This is the number of LH recombination events and number of Illy-Riddell recombination events. And the next slide is the same, but with reactions which led to NO production. Again, great agreement between 1 processor and 3 processor case for the fraction of occupied active sites, and also very good agreement between this 1 processor and 3 processor case for the number of Link-München-Schulwood recombination events and Illy-Riddell recombination events. The next verification case is the 2D airflow around a circle cylinder for parameters which are typical for the re-entry at the altitude of 85 kilometers. We consider different models of surface chemistry here. This is the translational temperature flow field. And you see the comparison for this is for the RCG Deutschmann-Riedel-Warnitz model. You can see the comparison between 1 processor case and 72 processor case. These are the mass fractions along the stagnation streamline. You see this great agreement. And this is the non-dimensional heat flux over the cylinder surface. Again, they are in agreement. This is similar results for Kovalev's model of alpha alumina. And again, 1 processor case and 72 processor case are in perfect agreement. And this is the results for the Kuratake model of CO2 with NO production. Probably you see some difference only between one processor case and different multiprocessor case, 18 processors, 36 and 72 threads. Probably we should look closely at this one processor case, maybe why we have this small disagreement. But you see 18 processors, 36 processors, 72 processors, they coincide greatly here. And finally, we try to apply it, this approach to simulating the air thermodynamics of the Apollo command module for different surface chemical models. This is we used almost 200 processors here. This is the temperature flow field for these computational results. What we obtain, these are the mass fractions along the stagnation streamline for different chemical models, and we see the effect of surface chemistry on the mass fractions. The blue curve is the non-catalytic case. The black is the Kurataki model with no production, and red one is the RCG model, and we see that we see the very clear effect of the surface chemistry, and RCG model gives more pronounced effect than Kurataki model. The same for the mass fractions of molecular and atomic oxygen, and for NO. Qualitatively, the results are the same. And the surface chemistry has an effect on the heat transfer to the surface. You can see the comparison of distribution of the non-dimensional heat flux. Left parts are non-catalytic case, and right parts are different surface chemistry models, and we see the difference between the non-catalytic case and the catalytic case. And in this slide, we see the distribution of the heat flux in the cross section between the heat shield and the plane of symmetry. And this effect of surface chemistry is clearly seen here. Recall that this is a computation for very high altitude, 100 kilometers, and even at such high altitude, we see the effect of surface chemistry. If we take a look at the total recombination rate, which we calculated directly from these simulations, we see that Link-Mürchenschelwood recombination dominates at such parameters. At such flow parameters, and the total effect, or in the stagnation point, the total effect of the surface chemistry is between 7% and 15%. We can expect high effect at lower altitudes. And if we use the radiation adiabatic boundary conditions on the surface, when all the heat flux from the incoming and reflected molecules and from chemical reactions is in equilibrium with the radiative heat flux from the surface. So in this case, we have a very pronounced effect of the surface chemistry on the distribution on surface temperature, as you can see here. It can reach almost 1,300 K for the catalytic RCG case here. And we see the comparison of the temperature distribution between non-catalytic case, left parts of both plots, and the right parts are different chemical models. And finally, I'm coming to the conclusions. We developed an approach, an algorithm of parallelization of DSMC surface chemistry based on the detailed macroscopic models we implement this algorithm into the SMILE++ code and verify it, but by comparison with a single processor computations. And finally, we successfully applied it to 3D computations of space vehicle thermodynamics. Thank you for your kind attention.